Hey Algebras! So here is your Unit 8 sequence and series review, and these are your post-it formulas. I kind of prefer to have them on actual post-its so I can carry them with me and do all my problems. So I'll let you take a peek at this. This is what we did in class on Tuesday with third period. So if you're a second period friend, hopefully you tried this. And you can check your answers. If you have questions, make sure you bring them up in class tomorrow. We'll get busy starting on the next couple of problems. Ready? Let's go. So I can tell right away that these problems are a little bit different because I'm looking at plus signs in between my terms instead of commas. So when I look at what kind of a situation I'm looking at, my dots here let me know that this is an infinite relationship, but notice no dots. So here's our first example of a finite relationship or a finite pattern. Those plus signs are going to let me know that this is not a sequence, but actually a series. I still go about this the same way, looking for the common difference or ratio. So when I look at how do I get from one term to the next, as I look here, it looks like I'm going to be subtracting 4 each time, which makes this an arithmetic situation. So we'll go ahead and make sure everybody knows that that's arithmetic. When it comes to writing the rule and some notation, I actually have to do both of these in order to get that done. I'll show you how. I'm going to pull my post-it note up because when I want to write the rule, I'll know that any number is equal to that first term plus my difference times n minus 1. So any number that I'm looking for is going to be my first term 1 plus my difference times n minus 1. Now with arithmetic sequences, you know we can simplify. So we'll say that any number is equal to 1 minus 4n plus 4. Any number is equal to negative 4n plus 5. And I always like to just plug my first term in and test it. If I put a 1 in for my first term, is that going to be, or this 1 for my n is my position 1. If I put that in, negative 4 times 1 plus 5, do I get that first term out? Yes, I do. So we're good. So here's where the summation part comes in. So this here is our rule, and we can make sure that we know that. But here's how we want to find the sum. If I want to write it in summation notation, that's when I write that sigma, and I represent how many of these numbers I'm going to be writing. So if this is my first term, here's my second, here's my third, here's my fourth, and here's my fifth. So sometimes you see this with an I, sometimes with an N, nobody cares. Whatever variable you use here, you use in your rule. And you let everybody know that you're adding up the sums of the first 5. 1, 2, 3, 4, 5 terms. And you want to know that the rule is going to be this. So if somebody came upon this, they would say, oh, we'll put a 1 in, get this as an output. We'll put a 2 in, get this as an output, and add them together. We'll put a 3 in, get this as an output, and add them together. We'll put a 4 in, get that as an output. Put a 5 in, get that as an output, and we'll add all these together. And you're like, what a colossal waste of time adding all those numbers up. Well, when there's only 5, you're right. It is a waste of time, and we can do it. But check this out. They want us to find the sum of the what? First 20 terms. And that's where these come into play. So remember, these two formulas are a hybrid. So here this tells me what any number is, and this tells me what the sum is. And if you look at this a sub n, this whole formula is substituted in there. So this is going to be the one that helps me when I don't know what my last term is. So I know the sum of the first 20 numbers is equal to 20 divided by 2 times twice my first term. My first term is a 1. And that's going to be plus that common difference of -4 times however many terms I'm adding up -1. And sometimes before we jump to the calculator, it's easiest to go ahead and simplify some of these terms or some of these things. So I know that 20 divided by 2 is 10. I know that 2 times 1 is 2. And then I have -4 times 19. So just by doing some of that math, I made what I type into the calculator a little bit simpler. All right, so we'll go ahead and say, what is 10 times 2 plus -4 times 19? Make sure you close those parentheses. So so the sum of the first 20 terms following this rule is going to be -740. Now let's be clear what we're talking about. We didn't need the rule to get this answer. We did need the rule to write it in summation notation. So these problems are pretty chunky. They've got a lot going on. If they ask for my rule and my summation notation, here's this part. And then here's where I'm going to use this formula. And it's so important you understand that this formula is really just the combination of these two. All right, we'll move on and look at our next one. Here we have an infinite series because we see those 3 dots. And I know it's a series because things are being added. So when I'm going to go ahead and look at what's going on here, as I look at what's going on from one term to the next, I notice my friendly numbers of 4. And I'm wondering, okay, what is happening here? How do I get from here to here? So if I have my second term divided by my first term, that's what's going to give me my common ratio. Now, if that doesn't make sense to you, go ahead and type it into the calculator, because you can look at 3 divided by 4, and that's divided by 3. I don't know why I wrote a 4 there. That's divided by 3. 0.25. So you know that that's 1/4, which means that I am multiplying by 1/4 or dividing by 4, however you want to write it. So I know it's a geometric sequence. I know that my common ratio is 1/4. And if you notice, this makes sense as I keep going through that series. All right, let's write my rule or summation notation. So when I want my rule, I know that any number, and I'm going to go ahead and get my post-it note for my geometric series, any number is equal to my first term times my ratio to the n minus 1 power. This ratio should be smaller. Okay, so any number is equal to my first term was 3 times my ratio is 1/4 to the n minus 1 power. Guess what? I can't simplify that. This 3 and this 1/4 can't be multiplied until this exponent is dealt with. So when I'm looking at my rule, there it is. If I want to put that rule into summation notation, I'll go ahead and say, okay, the sum, and I'll start with my first term. Here I go. My n is equal to 1. And here's my second, third, fourth, fifth. But guess how far I'm going up? To infinity. So I'm starting with my first term, and I'm going up to infinity. And I'll write my rule of 3 times 1/4 to the n minus 1 power. So I can write that in summation notation. That means I'm asking for the sum of all of these values from 1 to infinity, on and on. So some think that that's easier than writing out this rule. So that's going to be my summation notation of my rule. Now here's the part that I need to make sure you understand. when somebody asks for the sum of the series, it all depends on this R. If my R is less than 1 and greater than 0, I can find that sum. And here's why. Take a look at each of these fractions. As my denominator gets bigger and bigger and bigger, the value of my fraction gets smaller and smaller. So eventually, my sum doesn't really change once I keep adding pieces on. So that's when I get to use this formula here, a sum of my infinite series. So the sum of the infinite series is going to be equal to my first term, which is 3. There he is up there. And that's going to be over 1 minus my ratio, which is 1/4. Okay. So the sum of my infinite series is going to be equal to, and I'm going to jump right to my calculator, and I'll say, okay, 3 divided by, and I'll put this 1 minus 1 divided by 4 in parentheses, and then I'll know that that sum is going to approach and get closer and closer and closer, so it might as well be considered 4. Kind of cool when you think about it, because you're adding each of those little itty bitty 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 pieces. All right. So here comes this next one. So we'll take a look at it. Let's start examining first. The first thing I look for is going to be my dot dot dots. There they are. So I know it's an infinite relationship. I see my pluses, which means I know that it's going to be a series. Now my decision is whether it's arithmetic, geometric, or neither. So I look here, and for me to get from -5 to +10 is plus 15. If I add 15 to that, no. So it's not arithmetic, there is no difference. Let's take a look here. For me to get from -5 to +10, that's times -2, times -2, and times -2. I think that looks right. So it's a geometric series, and my R is a -2. Let's go ahead and write the rule for it. I know that any number is going to be equal to, and here I go again, I'm going to get my post-it note, because that's helping me every time. Put it over here. Any number is going to be equal to my first number times my ratio to the n-1 power. Okay, so that means that any number is equal to my first term, which is -5, times my ratio, which is -2 to the n-1 power. And again, I'm done. There's no simplifying for me to do for this one. So my rule is done. All right, if I ask for summation notation, that means that they want me to bring in the sigma, and they want to say, hey, where are you starting? And n is equal to 1, that's where I'm starting. And where are you ending up? Oh, I'm going all the way up to infinity. And how are you getting there? Oh, we're going to take -5, we're going to multiply it by -2, and we're going to take that to the n-1 power. And then this represents those sums I'm adding as I go, which is why I have that sigma there. So then somebody says, oh, that's a lovely rule. Will you please tell me the sum of the first 10 terms? And you're like, wait, can I do that? Yeah, because even though it's an infinite series, this tells you where to stop. So when I go here, I'm looking for the sum of my first 10 terms. It's not infinite, it's my first 10. So the sum of my first 10 terms is going to be equal to my first term, which we know is -5, and that's going to be times 1 minus my R is going to be equal to that ratio, -2 to the nth power, all over 1 minus, and my ratio is going to be -2. Now, typing these into the calculator is definitely tricky. Lots of parentheses, make sure that you get it all covered. So we'll walk you through each step at a time. Ready? Okay, So first we're going to start with our negative 5. So negative 5 times. Next we're going to start with our numerator. So we're going to start with that parenthesis 1 minus, and we'll go ahead and put negative 2 inside the parenthesis and say that's to the 10th power. And then what we need to do is close the parenthesis for our numerator, do the division, and this is going to show our denominator is 1 minus negative 2. Now when we close this parenthesis, oh, I forgot it. Darn it. Parenthesis 1 minus negative 2. So this parenthesis closes this, and then we need to come up with this parenthesis. See if I did that right. There we go. That's the sum of the first 10 terms of this sequence, of this series. 1705. Okay, how are we doing? Are you with me still? Here we go. Take a look at this one. Would you say that it's infinite or finite? Yeah, those dots will tell you that. All right, now is it a sequence or a series? Series, because I see those plus signs. Do you? Okay, now let's look at how we get from one to the next. So negative 3 up to positive 2, that would be a change of plus 5. Here's plus 5, and here's plus 5. It looks like it's arithmetic, and the rule is plus 5. So it's not geometric, and we don't need to look for an R. All right, let's write the rule. So because it's arithmetic, I get that posted out. So I know that any number is equal to my first term, which is negative 3, plus my difference, which is positive 5 times n minus 1. So because it's arithmetic, I can do some simplifying. Any number is equal to negative 3 plus 5n minus 5. Any number is equal to 5n minus 8. So you know what I like to do, plug in my first term. Does that give me a negative 3 as an output? Yeah, that works. So I know I did it right. Okay, but I'm not finished. It's a series, not a sequence. So I got my rule down, but now I need to do my summation notation. So there's my summation notation, and I know that from my first term up to infinity, so my first term up to infinity, and that is going to be equal to 5n minus 8. That's my rule for what's going on, right? There's my summation notation. Guess what? They want me to find the sum of the what? First 100 terms. Shoo-wee. All right. So since I know that it's arithmetic, I'm going to look right here and say the sum of the first 100 terms is equal to those 100 terms divided by 2 times twice my first term, which is negative 3, plus my difference, which is 5, times my n number, which is 100, minus 1. Sum of the first 100 terms is equal to 50 times negative 6 plus 5 times 99. Now, they love to put this problem on the SAT because it's a problem that if you don't know the formulas, you will spend a very long time adding up a bunch of numbers to get to where you need to be, and you waste all that time instead of doing your next math. Let's see if I typed everything in right. Looks good. All right, so the first 100 terms of this arithmetic series is 24,450. All right, let's take a look at these next two. You know what to do. Look for the dots. Once you see the dots, you know it's infinite. No plus signs, so you know it's a sequence, not the series. So let's take a look at what we're doing here. And if you want to know how do I get from one to the next, you can subtract these two. So this would be adding 1, and this would be not adding 1. So I don't think that's going to work. So let's see mathematically, and I'll prove to you. Ready? So if you had 3 divided by 2 minus 1 divided by 2, there's my 1. And if I have 3 divided by 2 plus 1, does that get me to my next term? No, because 2.5 is, and if I want to prove that, oops, math frac, see, it's 5/2. So it's not arithmetic. There's no difference. Okay, so if we want to know how to get from here to here, try it. 3 divided by 2, and that's going to be divided by 1 divided by 2. I might need some parentheses here. So it looks like 3 might be my common difference, or my common ratio. Does that make sense? Times 3, times 3, times 3. That looks good to me. It's a geometric sequence. All right, I don't need to worry about summation notation because it's not a series. So here's my rule. Hey, any number, it's geometric. I'm using this post-it note here. Any number is going to be equal to my first term, which is 1/2, times my ratio, which is 3 to the n minus 1 power. And that's it. I don't need to simplify it because it's a geometric and I can't simplify any of that. Okay, now it says, oh, I don't want you to find any number. Hey, will you please tell me what the 30th term in this sequence is? You're like, absolutely. It's 1/2 times 3 to the 29th power. So we can do this in any order we want. 3 to the 29th power is that. And then if I want to times 1/2 or divide by 2, I can do that. So our answer is a pretty big number. It's 3.43, we'll leave that, times 10 to the 13th power. That's what that times e to the 13th power means. So if we wanted to 343 and move our decimal 13 decimal places, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's a pretty big number. So here's my hundreds and thousands and millions and billions. So it's 34 trillion. Did I do that right? Yeah, 34 trillion, 300 billion, 300 billion is the answer. That's my 30th term. My 30th term. It's pretty high. Okay, here we go with our last one for this page. Hope you're still with me. Do you see the dots? No. So it's a finite relationship. Let's see what's going on. I wonder if this is, so 24, I'll clear this out so you can see what I'm doing. 24 minus 6 is 18. 24 plus 18 does not get me to 96, so it's not arithmetic, and there is no common difference. And it is a series because I see those plus signs. So 24 divided by 6 is 4. All right, let's see, 24 times 4 is 96. So it looks like my ratio is times 4. All right, let's write the rule. Any number is going to be equal to my first term, which is 6. Here's my post-it. Make sure you can see it. There we go. 6 is my first term times my ratio, which is 4, to the n minus 1 power. So, and again, I can't simplify that because this exponent in the order of operations comes first. So now we'll go ahead and write my summation notation. I did my rule. Now let's do my sum. So my sum of my numbers, and I have 1, 2, 3, 4. So from n is equal to 1 all the way up to 4. And my rule is 6 times 4 to the n minus 1 power. And that's my summation notation for that geometric series. If it's asking me to find the sum of the series, now here's the thing, it's pretty easy. You can just add doop, doop, doop together. But if you want to go ahead and find the sum of the series, you can. You can say that the sum of the first, what's that, 4 terms, is going to be equal to your first term, which is 6 times 1 minus your ratio to the 4th term. And that's going to be over 1 minus your ratio, which is 4. Now, I got to be honest with you. This one is probably going to be easier to just add these numbers together. 6 plus 24 plus 96 plus 384. So I'm looking at 510. Now the goal is test yourself. See if you get 510 when you enter these values into the calculator. Ready? So we have 6 times, and my numerator is going to be 1 minus 4 to the 4th. Close that. Divide by, and my numerator is going to be 1 minus 4. Close that. And we should get 510. Good news. So we know we did it right. All right. So that's it for the first part of this review packet. I'll go ahead and post this video. And we're going to do the second part in class tomorrow. And then I'll post that key and check it out for those of you that are not in class with me. All right. Keep working.